Hello, everyone, and welcome to my capstone project presentation, Factor Timing, a machine learning approach for dynamic allocation to Fama-French factors and momentum. I'll explain how we can use advanced machine learning techniques to time investments in factor-based ETFs, enhancing return and minimizing risk. Let's dive into the future of investing, optimized by machine learning. We are Team 4522. Sandeep and Omar are my beloved teammates who made invaluable and fundamental contribution to make this project happen. My deepest gratitude to them. I would also like to thank Prof. Joe Byers for his strategic guidance as our mentor. Factor investing targets attributes like value or momentum for enhanced returns. Our goal is to perfect the timing of ETF allocations, a challenge with traditional methods. By using machine learning method, we'll systematically determine factor ETF weights and allocation timing, provide a data-driven, adaptable investment strategy. In our literature review, the innovative work of Volatility on deep reinforcement learning stands out, showcasing how advanced algorithms can be used to understand factor investing dynamics. Similarly, the use of stock graphs, as explored by Wei and his team, underscores the importance of capturing the complex relationship between market factors. However, challenges remain, particularly in translation of the sophisticated models like autoencoders, highlighted in the research by Colin, and LSTM RNNs, whose potential was demonstrated by Hochreiter and Schmidt-Duber, into interpretable strategies for ETFs. These advanced methodologies have carved a path for extracting economic value from latent factors and refining factor beta estimates. Still, as we look into the work of the experts like Cullen, Thomas, and Cotter, we find that the field requires further breakthroughs in dynamic factor analysis and the clarity of machine learning applications. In examining the real market, we focus on 3 ETFs addressing factor investing, 2 passively managed under a set of rules, and 1 active managed by BlackRock. As you can see from the SWOT analysis, pacer ETFs excel with a simple yet effective approach, while Volatility offers a broad range of strategies with mixed results. BlackRock's active strategy has yet to outshine its benchmark. While pacer ETFs perform well, the simplicity of their method poses a risk of imitation and factor crowding. Volatily's complexity could confuse investors, and the poor performance of their macro strategy is very notable. BlackRock's active management has not translated into expected performance gains, questioning the value of higher fees. Crucially, none of these leverage on machine learning. This is an opportunity for us to innovate with an AI-enhanced model, setting a new standard in factor investing strategy. Our assumption will be that our chosen machine learning techniques, ridge regression, random forest, XGBoost, and MLP neural networks, are not only suitable for our problem statement, but their performance will be quantifiable and robust. In addition, we also assume the model's ability to generalization is good. We've opted for Python because of the rich collection of libraries that are essential for machine learning, such as Pandas, NumPy, Scikit-learn, and TensorFlow. Our machine learning libraries we also assume they are diverse and offer well-optimized implementations that can handle our complex financial data effectively. We've taken the feedback from our peer review seriously and made several key incorporations to strengthen our work, recognizing that the risk of overfitting we've added a more robust out-of-sample performance evaluation. We'll also focus more on challenges and limitations for the literature review, offering a more comprehensive discussion that lends greater depth to our analysis. Lastly, we've also incorporated visualization and graphical representation to improve the interpretability of our findings. This is a summary of our methodology. In our approach to data creation, we start with Fama-French library, a gold standard in financial modeling. Following rigorous exploratory data analysis, we ensure our dataset is ready for future engineering. We draw on techniques suggested by James in his book of An Introduction to Statistical Learning to introduce lagged returns and rolling statistics. To visualize our correlation, we crafted a heat map as shown on the right, giving us a clear picture of factor relationships. Our modeling framework employs a variety of machine learning models. We integrated the robustness of ridge regression as outlined by Hoare and Kinnard, with the versatility of random forest championed by Bruman, XGBoost, inspired by Chen and Goldstein's work, and neural networks following Goodfellow, Bingia, and Covey's deep learning principles. Our project's initial goal were to enhance factor allocation using machine learning. With ridge regression, we achieved a respectable mean square error, or MSE, for 0.037, as shown in figure 3. Momentum was a key player in our allocation, emphasizing its influence in the financial landscape. Shifting to random forest, we further reduced the MSE to 0.0336. Figure 4 reveals a more volatile allocation, suggesting a strategy that may require more active management. This volatility highlights our work's novelty in capturing market dynamics and its importance in quantitative finance. We've learned that momentum remains a cornerstone, but its role varies across different models. Continue our result review. XGBoost mirrored random forest performance with an MSE of 0.0633 and a similar allocation pattern as shown in figure 7. The MLP neural network somehow presents the highest MSE of 0.0574 with a very drastically different allocation as shown in figure 9. Here, momentum doesn't dominate. Instead, we see a more balanced weight distribution. In the backtesting out-of-sample test, neural networks, even though having the highest MSE, particularly outperformed in these out-of-sample tests, showing the with the highest cumulative revenue. So it showcased the unpredictable nature of financial markets and the power of complex models. It's crucial to recognize our factor returns operate within market-neutral strategies, making absolute performance comparisons more meaningful than relative market comparisons. Our contribution is clear. By integrating machine learning, we provide a fresh perspective on factor investing. The neural network's unique allocation strategy demonstrates our model's versatility and underscores the importance of diversification in financial decision-making. Our lesson: each model has its strengths, and a blend of approaches may offer the best real-world utility. As a highly collaborative team, we jointly developed the core ideas and problem statement for our project. We maintain constant communication and support one another throughout the process. Yet, we've also clearly divided responsibilities, with each of us leading a major component of the project, as outlined in the table here. On top of that, I've taken on the extensive proofreading and seeking expert advice from seasoned industry professionals. leveraging my experience as a marketer in the banking industry. As we conclude our project, we find that neural networks have outperformed the other machine learning methods. This highlights their viability for tabular data sets, expanding their application beyond conventional users. Our research illuminates the importance of nonlinear interaction between factors, a significant departure from the linear foundation of the Fama-French factors. The predominance of interaction and spread features in our feature important plots confirms the critical nature of this nonlinear relationship. Moreover, our methodologies are not just theoretical exercises. They are practical and can be applied to long-only factor ETF, provided the factor returns align with systematic definitions. These adaptabilities ensure our findings have tangible benefits in the real-world finance landscape. Although the project is based on factors, the concept of timing can be extended to side segment timing and thematic fund movement. They can potentially enhance commodity price and price analysis and improve risk management, particularly with outliers. This opens new avenues for applying machine learning in finance. This is the end of the presentation, and I would like to extend my heartfelt thanks to WorldQuant University. My gratitude goes out to Dean Gabrielle Meolo for her great leadership, and our dedicated faculty who have shared their knowledge and wisdom with us. Lastly, my thanks to the support team who has been extremely accommodating and kind. Together, you have created an environment where curiosity thrives and innovation is fostered. Thank you all for making this project and our growth possible with WorldQuant University.